Welcome everyone to lesson 2.9 from Precalculus, which is all about logarithmic expressions. So let's dive in. Our big idea for 2.9 is rewriting exponentials into logarithmic expressions or equations and vice versa. So we'll dive into exactly what is a logarithm later. For now, we're really just worried about the conversions between the two forms. And what we can see here is that an exponential in the form of b to the a power is equal to c can be rewritten. It's equivalent to log base b of c is equal to a. So what happens here is that the old base becomes the subscript of the logarithm. The exponent is what the logarithm is equal to, and the result of the exponential is what goes inside of the logarithm, which is also called an argument, but you don't really need to memorize that fact. So let's try this out and actually apply this. So if we have these logarithms here, how can we rewrite them as exponentials? So the first thing we're going to do is we're going to identify the base. It's always going to be the subscript, the small number here. This is going to be 3. Logarithms are equal to exponents. So they're equal to the exponent. The exponent is 4, and therefore the result should be inside. And this makes sense to us. 3 to the 4th power is indeed 81, because 3 times 3 is 9, times 3 is 27, times 3 is 81. Now, if we try out this logarithm, it's a little bit different, because we should get the base of 16, the exponent of 1/2, and the result of 4. How does this make sense? Well, remember, we talked about that rational exponents, the denominator of a rational exponent is the root. So this is asking what the square root of 16 is, and it's 4. So, not that bad. Let's go the other way around. If we have an exponential 125 to the 1/3 power is equal to 5, we're going to write the word log. The base of the exponential is the same as the base of the log, so the 125 is going to be the base of the log. We're going to write it as a subscript, so it's going to be small and like one layer down. And then we're going to put the result on the inside. So we'll put the 5 there, and it's equal to the exponent, which is 1/3. Now, do you need to put parentheses? Like, there's no parentheses up here, and I put some parentheses here. The technical answer is if you only have one term inside the logarithm, you don't really have to. But I like to a lot of the time, simply because it helps me stay organized. If I'm worried about speed, I won't include it, but if I'm worried about being able to convey my message to you, then I'm definitely going to try to include it. Last but not least is 10 to the 3rd power is 1,000. So this would be the log with the base of 10 of 1,000 is equal to 3. Now, I also might sometimes use a capital L. That's just semantics. It really doesn't make a huge difference. But that is the conversion. So going from logarithms to exponentials and then exponentials to logarithms. Not too bad. So we can evaluate these new logarithms by using conversion. So first of all, I see a log without a base, and that brings up a key point. If you see just the word log and you don't see a subscript, that is the same thing as base 10. So this is equivalent to log base 10 of 100. We don't know what this is equal to, so let's say it's equal to x. So we have log base 10 of 100 is equal to x. Let's convert this to an exponential. So the base of the exponential would be 10, the power would be x, and it would be equal to 100. And we can pretty easily answer this question. 10 to what power is 100? That means that x has to be 2. So this log of 100 is 2. We can continue with this one here. So we're going to set it equal to x. We're going to convert it to exponential form. So 2 to the power of x is equal to 1/32. And this one's a little bit harder to see. I don't really know what power this is, right? I do know that a fraction with a numerator of 1 comes from a negative power. So this would be 32 to the negative power, or the negative 1 power, if you will. And 32, is that a repeated multiple of 2? Well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So that would be 5. So this is equivalent to, or the 32 to the power of negative 1 is equivalent to 2 to the power of negative 5, which means that x is equal to negative 5. Not too bad. Now I spy with my little eye something different about the bottom two. If you notice, if I rewrite these as exponentials, I would get 4 to the x power is equal to 25, and I would get 10 to the x power is equal to 39. Those aren't pretty. There's not a nice power that works there. And when there's not a nice power that works there, we really don't have the tools. We're not well equipped enough to be able to answer this question without a calculator. So what you can do is you can get out any calculator. Your phone calculator actually will work too. I'll unlock mine right here. And if we turn it on, like if you have an iPhone, for example, if you turn it on its side, you can hit 39, hit the log button, and you can get an answer. So in this case, x would be equal to 1.591. How do we solve the other one? And to be honest with you, you don't have the tools besides using one of our fancy calculators. So if you use a TI-84, which we use in class, we have the option or the ability to be able to evaluate this. And what you would do is you would hit the math button, and then you would hit, or you would look for the words log base on the TI-84 in that math menu, and you will end up getting an answer. So the answer that I got was x is equal to 2.322. It rounds up. So what happens if you don't have a fancy, TI-84 calculator to be able to do that? Well, you have a couple of methods within your own toolbox you already have. And in class, I'm going to ask you to brainstorm some ways to actually be able to do this. So I don't want to steal that thunder. But if you have questions about it after that discussion, please make sure you ask. All right. Moving on, our last major thing we're going to talk about is some common logarithm bases. These are the ones that come up the most often, especially when you talk about applications of mathematics. And the first one is the common logarithm, which is the log base 10, which we already know. We can write that as log x. The next one is the natural logarithm. So we talked about Euler's constant, the natural constant, and its importance with exponentials. Well, it also has importance with logarithms as well. So log base e specifically of x, we can write as ln for the natural log. It's log natural first because I believe for the French language, but you don't have to quote me on that one. The last one is the binary logarithm, which is log base 2, which is dealing with like half-life and doubling and that kind of thing. So not really important, but I did find this out recently and I wanted to share with you. There is 2 other notations that are used for these common log bases. For log base 10, some mathematicians have written this and may write this as lgx, leaving out the O, and log base 2 doing ldx for doubling. And I just thought that was interesting to know, but it's not common. It's not something we're going to use in our class, but if you do happen to see those notations in the future, you do know what they mean and that kind of thing. I just thought it was cool. That is it for today's lesson. If you have any questions, please make sure you ask. Otherwise, I'll see you in the next video.